All right, so we're a minute past. I'm going to go ahead and get started. I really appreciate all of you who have taken the time so far to say hello in the chat. It's nice to meet you. My name is Denise Koessler. I run the data ops organization at DataStax. And during the session today, we're going to spend a lot of time modeling and seeing, and then eventually at the end, querying connected time series data within the power grid industry within the US for an application that I helped to build for a large power company in the United States. So for some of those, for some of you who have noticed, for a little bit of housekeeping items, I have the chat pulled up over here on one screen, and I'm happy to take questions as we go. So as you see my head kind of flipping between these two directions, I'm just watching between my slides and then also over here into the chat for questions. So I hope it's not too distracting for you all, but I love questions as we go. Tina, thank you. Glad to hear we're at a good start. So that's what we're going to be doing throughout the session. A little bit more about me. As I mentioned, my name is Denise Gosnell. I have worked with graph data and graph technology for over 10 years now, almost 15. Can't wait to get to say that. I have a few patents, many publications in unique applications of graph data and graph technology. Currently, I work at DataStax, where I'm the Chief Data Officer, and as I mentioned, I lead the data ops organization here at DataStax. And I have spent the past 10 years, almost 15 years, applying graph technology, graph algorithms, and graph data to solve complex problems in bioinformatics, telecommunications, the power grid we're going to see here, logistics, and many other companies around the world. I've been advising and helping build different applications for dozens of teams around the world, and I'm looking forward to bringing all of that expertise to this session here today. And most recently, I had a book that was released on Amazon that was the #1 new release in artificial intelligence. So I'm extremely appreciative for all of you who have already been supporting this work. It's been a really fun journey, and I'm glad to be bringing one specific part of that book to this talk today. So here's what I plan to get through, and hopefully we'll have all the time to get all the way down into the Gremlin code that we're going to be doing at the end. This is one of the longer sessions in case that might be something you were unaware of. So this session goes all the way up to 11. I'm going to try and close at about 10:50. So at about 10:50, I'll be wrapping up and taking a few questions, but I can also hang around for more questions afterwards. But largely, this is what we're going to be doing throughout the session. We're going to start high level with just a brief 5-minute primer on why graph technology and how I help businesses around the world think about when to use connected data and when to use graph technology. For one of those use cases, we're going to take a deep dive into the business use case for a self-organizing sensor network within the power grid in the US. So if you flick a light switch somewhere in the United States or in a surrounding area, you are contributing to one of the largest connected networks of distributed graph data in the world. We're specifically going to dive into the failure scenarios and how they're using graph data as a feature to be proactive in monitoring different network failures that occur. And lastly, we're going to walk through the data, and we're going to flip on over into a notebook, and we're going to walk through some Gremlin code. So for those of you who are new to graph data and graph databases, Gremlin is a functional query language, and it's going to feel and look a lot different than object-oriented languages. So for the computer scientists out there, there's going to be some really interesting ways that you can look at the mental model of the differences between functional programming and object-oriented programming that we're going to get to there at the end. But I'll save that there once we get there. I'm going to wrap up, like I mentioned, at about 10:50 and give you guys access to my book and different places to go get all the code and all the examples that you're about to see. Before we get all the way down into the weeds, I want to start up here because we do have some new people in this session who are new to graph technology. And I'm gonna put a story out there to talk about why graph technology, because to be honest, it's a complete accident that I am here today doing this session. And the story kind of goes like this. A little more than 10 years ago, I was starting my master's degree in mathematics, and I was locked out of all the required courses like number theory, abstract algebra, combinatorics. And so I had to take this elective just to fill my schedule, and the elective was called graph theory. And I'm not the kind of student who reads the book before class. So I went into class that day thinking we were going to be spending a whole semester talking about business intelligence, like bar charts and pie graphs. I know I didn't mean to be thinking that way, but I didn't know. And quickly, within the first few minutes of class, Dr. Teresa Haynes, who's one of the most well-renowned graph theorists of our time, she drew this picture of how everyone essentially is connected to their friends. And you can think of people as a vertex or a circle like you see on the left, and their friends are edges in this social network to other connections that they may have. So throughout the rest of my career, and then through this talk, whenever you hear me say graph, I'm talking about connections on the left, but not bar charts like I thought on the right. And as I have made this my passion and a cornerstone of every application I have really been getting into and building since then, I've helped kind of develop a mental model of how to advise teams and companies around the world of when and why you would care about graph connected data or using graph technology. And there's 4 questions that I really commonly I talk about and really have teams really lead teams through some difficult conversations. And when you're looking at your problem or the predictions that you're trying to deploy into production, whether or not graph data applies comes down to whether or not you have connected data. And that does make intuitive sense, but when you're looking at all of the technologies that you have, whether or not you add graph technology into your stack can be a big decision. And from the business perspective, you really have to dive into that second question here on this slide and understand whether or not relationships within your data help you understand your problem. So there's 2 quick examples to think about real fast. If you're on LinkedIn and you frequently find yourself kind of browsing other people's profiles and looking at your second and third connections and trying to tell a story about how you might know that person or how you might know the friends that you have in common, that is you intuitively using the connections between data. Or like most of us right now during COVID, we're probably on our streaming platforms like Netflix a lot more than usual. That recommendation window on Netflix for finding new content also is using connected data behind the scenes. It's looking at the movies that you viewed, the people that viewed those movies, and then also movies to recommend from that set. So it's looking at the relationships and the connections within data. Now, we're not going to be getting into how Netflix deploys that recommendation window. If you're interested, that is chapters 10 and 12 in my book. But for this one, we're going to be looking at, like I mentioned, the power grid industry. And where that fits in starts on this next section of the questions. So once you know that graph technology and connected data is required for your problem, I highly recommend that you kind of dive in and try and understand what you want to do with these relationships. And typically there's 2 common ways that people use graph technology in production. You're either using it to store and query connected data, or you're using it to analyze and run graph algorithms like Network X, which I saw on someone in the chat earlier mentioning that they like to use Network X. So if you're using Network X, you're squarely more in the graph algorithm section, maybe wanting to just do some general data science or feature extraction for your machine learning model. But for this example that we're going to be doing throughout, we are squarely looking at how a power company in the United States stores and queries their connected data within a distributed graph database. And they got to that stage because there's a specific feature that they need to extract for their failure scenarios. And that feature is most optimally extracted using connected data. So this example kind of squarely fits into the bucket of connected data is required, and we want to store and query it in a graph database. That's about as we're going to start from here, from the next sections. We're going to start digging much deeper into the example. And again, for those of you who joined after the introduction, I love seeing that we have many more people here. I'm monitoring the chat on this screen over here. So if there are questions as we go, feel free to ask. Happy to make this as interactive as possible. So the problem that we're going to be looking at for the next 40 minutes or so is a self-organizing sensor network within the power grid. And we're going to talk about where we find these graphs, and we're going to talk about how they work. I'm a very visual person, so we're going to see a ton of examples and we're going to walk through lots of images before we get into the code. We're going to start with giving you a picture on where we find these graphs. What you're looking at is a zoomed in section of Seattle, Washington in the US. And you're looking at two types of vertices, or two endpoints of data that happen in this connected network. They are sensors and they're towers. The orange asterisks across Seattle that you see on the image are the sensors, and the blue diamonds are towers. The sensors are outside every single home and business across every home and business in the United States. And we're looking at Seattle. So you all can already tell that I provided just a subset of the sensors for you to visualize here, because if I had all of them on here, it really wouldn't be possible to see them. The sensors in this network are the source of creating the self-organizing connected mesh network, because these sensors have two jobs. First, the sensor has to collect the voltage level of the home or business every 15 minutes, because it needs to know how much energy did this home or business use. Its second job is to ensure that that sensor reading, or that voltage level, finds its way to a tower. But these sensors do not always directly connect to a tower. They're going to create a Markovian network, or they're going to connect from one sensor to another, and they're going to pass the data payload from one to another until it eventually reaches a tower. They don't also connect to the same network the same sensor every time. One time, a sensor might connect to its neighbor on the left because it's available for transmitting communication, or it might connect to a neighbor that's in a different direction because it's available. So over time, these sensors create a dynamic mesh network. I want to put this into a video so you guys can really see this. And what you're going to see in this video is just a slice of time where the sensors are building up communication networks to other sensors. And eventually you're going to find that they pass this communication data to a tower. The sensors are in white, the towers are in blue. And what we're going to visualize during this, about 20 to 30 seconds in, is a failure scenario when a tower goes down. And when a tower goes down, the sensors nearby it that had directly connected to it are going to lose their connectivity. And that's the failure scenario that the power company was very, very invested in being able to identify. So as we watch this play, you're going to see some sensors start to collect that data and pass information to other sensors. As the dynamic network builds up, you're going to see that some of these sensors do eventually connect to a tower. There's a tower in the center section here that is going to go down. And those three sensors that are now orange are ones that are at risk of not being able to get their information to the tower. We were only able to determine that they were at risk because of the graph data structure, which is what we're about to walk through on how to do that. Once that tower comes back online, that group of sensors is able to successfully connect with the tower. And now what you're looking at here are just more communication on how the sensors and towers are forming this dynamic network, this self-organizing network over time throughout the city of Seattle. Can the payload get caught in a loop between sensors for a long time? Yes, it can. Because the only rule is that a sensor cannot send its payload to itself. It has to send it to a neighbor. So yes, over time, it can get pinged back and forth. That detail is getting into the specifics of the hardware implementation on how the sensor functions. And they do identify malfunctioning sensors with that loop. The level at which we're going to be working is how the power company takes this data and constructs the mesh network that is formed as they're doing this communication. And thank you for the question, Andrew. Another great question for those that are new to graph theory and graph databases is their introduction to database structure that you would use. There is an introduction to database structures in my book, and I'm providing a free access code to that here at the end of this. And you're going to be going through here in a moment an example of how to model this in a graph database, and then how to use it, load data, and query it and everything. So for those of you who are new, you're going to get all the way down deep dive into modeling, setting up your schema, and querying graph connected data. So it'll be all the way through a real quick introduction. So in that last video, what was most important was to start to understand that as these sensors are connecting to each other, there's failure scenarios that the power company most cares about. And yes, the payload getting caught in a loop is a potential failure scenario, but due to governmental compliance, they get fined, these power companies get fined if they do not have real-time connectivity or near real-time connectivity to all of the sensor information around their network. So the more important failure scenario is that these companies are very, very concerned about what happens if a tower goes down. So if a tower were to be taken offline, either for maintenance or because of a natural disaster in the area, they need to know as quickly as possible which sensors that they need to triage to make sure that they get them back connected to the network as fast as possible. There are 2 graph queries that are required in order to answer that question. You have to go in the past, you have to retroactively look at that tower and find out all of the sensors that connected to that tower. And then for each sensor in that set, you have to figure out if there were any other towers by which they were able to communicate in another window of time. A sensor that is at risk is a sensor that only uniquely communicates with the tower that is about to go down. Yes, the payload can be routed to a new tower using a new path. That's a great question. So let's go ahead and take a look at a failure scenario and exactly how that payload is rerouted. Great question. So we're going to zoom in here into just the lower Seattle area right above the Seattle airport. And let's just kind of look at the answer of what happens. So if that orange tower that you see here in the center of the image, if that goes down, you might think that the ones that are going to be at risk are the ones that are like directly connected to it or directly next to it. And it just so happens that that isn't true. Because of the dynamic nature of how these networks are formed, every sensor in orange is a sensor that was at risk because it had uniquely communicated the hour before that tower went down. That was just the hour before. If you look back, because the payloads can be routed elsewhere, some of these orange sensors did have successful connection to other towers. But what this does give is it gives the power company a smaller set of sensors to specifically go investigate or to triage over time instead of exploring the entire area, because we're talking about a sensor outside every home and business. So we want to make sure we're zooming in on a list that is much smaller than just everything. In order to identify what those at-risk sensors are, there's a series of really valuable questions that we have to ask. And at the end of the day, the biggest question we're looking at is what sensors are at risk when this tower goes down. And we're going to break that into 2 questions, as I mentioned. The first thing we need to do is for that tower, we need to know which sensors sent information to it in a window of time. We're going to end up with a list of sensors. For every sensor in that list, we need to ask the second question. To what other towers, for every single sensor in that list, did they send their data payloads? If there is a sensor in that list where it is only uniquely communicating via the tower that just went down, that will be a sensor that we need to investigate and reroute to ensure that that data is successfully transmitted back to the database. Fantastic. Thank you so much for the question. What is a tower? I've skipped over that. I appreciate it. So the tower in this example is just a cell phone tower. The power companies use the cell phone networks to transmit this information back to the database. Thank you very much. Great question. So let's take a look at an example so that we can kind of see exactly how these payloads are getting rerouted. We're zooming into downtown Seattle now, and you have 3 towers. You have the Westlake cell tower, the First Hill cell tower, and the Seattle cell tower. These are actual real cell towers that are live in downtown Seattle. What you have here is a subset of about 14 different sensors, 15 labeled A through S. And what you can see is how these sensors are forming communication networks that are passing information to a tower. So let's look at that first question. Let's look at answering, or how we would answer the question, what sensors sent information to the Westlake cell phone tower? So this Westlake cell phone tower is in green in the center. And you can see if you walk out one neighborhood if you walk out one edge, you'll find that sensor A in the upper left, B in the upper center, C, F, now I'm kind of walking clockwise, C, F, E, G, and D. All of those sensors directly connected with the Westlake Tower. From that set, you want to walk out one more level. And you want to say, well, which sensors pass their data to that set? And so now we're walking out two neighborhoods of data. And you can see first in the upper right that sensor N communicated with C and F. And via C and F, that's how the data got to Westlake. The same thing for sensor I. Sensor I went to F to Westlake. Sensor K went to K, E, Westlake, K, H, E, Westlake. There was multiple paths that you can see there. And you can kind of follow it along. So for the question of which sensor sent information to this tower, you walk from the tower and you walk backwards in order to find every single sensor that was on a path that communicated to the tower. There are not going to be duplicates for the actual application that we have running in production. All of these communication lines are time-based. So a sensor only sends one payload on a time interval. But for what we're walking through here, we're going to understand all the concepts without considering time. And if you are interested, the next example I can point you to shows you how to apply all of this and use time. So that's how you answer the first question. From the tower, tell me all the sensors that connected to it uniquely. And now we need to go the other way. We need to say, for a sensor, which towers did it send information to? And we're going to follow the paths for just one sensor. Let's look at sensor S in the lower right-hand corner, S for start. And there's many paths. You can find a direct path from S to the Seattle Tower. You can find a path of length 2 from S to A to First Hill. You can find a path of length 3 from S to A to C to First Hill. A path of length 4 if you keep going from S, A, C, D over to Westlake. And paths of length 5 and longer where S found its way to communicate with the Seattle Tower all the way through E, F, G, and things like that. Now, since these are just different paths based on time, we're looking at a snapshot where all the paths are aggregated together. And that's how we're going to be using this data in this example. So kind of looking over here, great question. Thank you so much for that question, FT, about duplicates. Andrew, sounds like querying node topology networks in Oracle Spatial. Is that similar to calculating routes in road networks? Calculating routes in road networks, I see as a different style of graph problem. I see it as a pathfinding optimization where you're doing shortest path point to point across a network. That type of problem is typically pathfinding point to point. This problem that we're looking at is what we would classify as a hierarchical or tree-like structure, where you are starting at a root and walking down to all of the leaves. So that would be starting at a tower and walking out to all of the sensors, or going from the leaves up to the root, starting at sensors and walking all the way up to towers. In the book that I was talking about in the beginning, we walked through the 4 common patterns of graph applications that use graph database technology. This example you're going through here is the second most common pattern of using hierarchical data or trees, roots and leaves. You get into these really fun terms that graph theorists and mathematicians introduced into the technology. And the one, Andrew, that you're talking about is pathfinding, the third most popular. Great question, thank you. COVID contact tracing is the same, I would think, as path to path or point to point path-based finding. And these are great questions. I'll be sure to take more of these as we go throughout the end, because I absolutely love how you all are thinking about different uses of graph technology. But what I am going to do is keep moving through the data encode for the sensor network example that we have here. So for the next, looks like 25 minutes, what we're going to do is we're going to look at the data that I have for this example. We're going to walk through the schema code for creating a graph schema based on the data model. I'm going to show you how we load it into the database. And then we're going to flip over into a notebook and we're going to query it. And we're going to do the query walking from a tower. Actually, we're going to do the one that walks from the bottom, from the sensors, and we walk up 2 towers. So we're going to start with doing the second query. So let's start with looking at what the data looks like. So for this example, in a GitHub repository, if you go to the GitHub repository now, since I know you all have web browsers open, all of the code and data that you're looking for is in chapter 6. So I'm giving you all a deep dive right into chapter 6 of the book. The data looks like this. This is a tower file. You have the tower name and the latitude and longitude. And yes, these are real cell phone towers, and that's their real cell phone or the cell phone. That's the real latitude, longitude geolocation within the Seattle area. There's, I think 270 some towers. And then the edges essentially represent communication. And so this is specifically communication that's happening between a sensor and a tower. So what you see here is that on the first line, you have a sensor that is numerically named, numerically partitioned. Sensor 103.318.117 communicated directly with the Bellevue Tower. And that time step here in the middle is where time shows up in the data, but we're not going to be using time in the queries here in the upcoming demo. You can also walk through and you can find other sensors that are communicating at a certain time with these towers. There's also a sensor file, a sensor edge file, where sensor 103.381.117 communicates with other sensors at a certain time. On this screen, we're just looking at the sensor to tower communication. So as we've been walking through this, and as you've seen a few times now, we have a basic graph database model. So for those of you who are new to graph databases, the first place that you typically want to start is how you want to model your data in your database. And you're looking at a basic model here. And there are 3 things you're going to have in a database model. You're going to have vertex labels, edge labels, and properties. The vertex labels you see here as the circles, or they're the sensors and towers. They're going to be your vertices. These are your vertex labels. The edges are going to be the links or the connections between the vertex labels, which we call send in this example, because we're sending communication from a sensor to a tower. The last thing that you see here on this graph model are properties. We have a sensor name, and that's going to be the full primary key, and a tower name, and that's going to be the full primary key for towers. Here's how you would write the Gremlin code for creating this schema in a database. And specifically, the database that we're working with is DataStax Graph. It's a distributed graph database that uses Apache Cassandra as its backend, where it uses the partitioning and table structure to have a fully native distributed adjacency list in Cassandra. This is not a vendor talk. So I don't want to really get into those details because all of the concepts we're talking about abstract to Neo4j, they abstract to Cosmos, they abstract to any other type of database. So I want to stick at that level. What you see here in this code, though, is how you'd actually create that vertex label. That top line is labeling your table or labeling your vertex label as a sensor. It's identifying its unique key with the partition by syntax. It's going to be a sensor name. And then we have the properties that we saw, the lat and long locations of these sensors, and same for the towers. The next piece of schema to create is to connect your sensors together with your edge label called send. And that's the first example here. You have a schema, you use the schema syntax, and you create an edge label called send. And then you say from and to which vertex labels that we're connecting. So we're going to go from the sensor to sensor. So this is going to be a self-referencing edge label. Now that's different from the duplicating comment with sensors sending information to other sensors. We can detail that when we look at the data here in a second. The second edge label you see here is an edge label from a sensor to a tower. So this edge label is going to connect the sensor vertices in the database to tower vertices in this database. Thank you so much, FT, for providing the link to the code. I really appreciate it. So in that graph in the code here, when you go into the data section, you will find the shell scripts that load this data into the database using DS bulk. Now, if you want to go into all the details of how to do this, this is where you would go. But we also have a Docker container that just auto loads and spins everything up for you, so you don't have to get into this detail. But what we're doing here is we're taking that tower CSV, where we had the tower name and then the lat long, and we're using that entire file and loading it into the tower schema that we just created on the previous slide. The next one, we're taking the communication CSV of sensors sending communication to towers, and we're loading that in as an edge. So on this second example, on line 5, you see here that we are saying to the database to load the sensor send tower CSV. Line 6 says that we're putting it into a graph called trees development. Line 7 is saying that this data represents an edge. That's the -E flag. And then we provide the edge label's name, which is send. Line 8 says which vertex that this edge is going to start. And line 9 is saying which vertex this edge is going to end. So edges start from a sensor and they go to a tower. And I provided headers in this file, so that's why we have header true. And the headers in your data files, if you like to load data this way, your headers in your data file have to match the property names in your database. So in this upcoming notebook, we are going to walk through the second question: to which towers did this sensor send information? And we're going to break that down into 4 steps. The first thing we're going to do is we're going to pick a sensor, and we're going to look at its first neighborhood, and we're going to say, well, which sensors or towers did this sensor directly communicate with? And then we're going to kind of progressively build up an understanding of our data. We're going to walk out to the second and the third neighborhood, and we're going to take a look at the data. And then we're actually going to create a recursive query so that we start at a sensor and we walk up to any tower. And in order for that to not get stuck in the loops, so that was a fantastic question about data duplication and communication happening between sensors. That's called a cycle. When you end up starting at like a sensor 1, sensor 2, sensor 3, back to sensor 1, that's called a cycle. So for looking at how these sensors communicated, how this sensor communicated with towers, we're not going to consider cycles. So once we find a cycle, we're going to remove that from the payload. And then at the very end, we're going to look at, depending on time, we're going to look at different ways to shape your data payloads of your Gremlin query results. I've got some tips and tricks from having worked with Gremlin for the past 6 or 7 years on how you can write try catch statements or if then else kind of statements. So that's the 4 steps we're getting ready to go do. And I'm going to show you the answer as a picture, and then we're going to go query it. So we're going to start with sensor 1002688. I'm just going to call them 688 from here on out. The first neighborhood is what you see on that first level. We're going to walk out the first neighborhood, and we're going to find the Georgetown Tower, and we're going to find sensor 508. When you walk out the second neighborhood, we're going to now run into White Center, 1061624, and then 1307588. When you walk out another neighborhood, that's when we start creating cycles, because from 1307588, there's an edge that goes back to sensor 103508, and there's also a connection where it goes back to the beginning. So what we're going to do in our Gremlin query is once those traversers find a cycle, they're going to be eliminated from the results because that's not helping us get to a terminal point. And we're going to keep walking recursively throughout our graph data structure until we find all towers. So without any further ado, let's go ahead and take a look at this. All right, if you guys could just let me know if this is large enough so that you all can see the code that we are getting ready to walk through. I'm happy to make it a little bit bigger if we need to. But what you're looking at here is you are looking at DataStax Studio. And DataStax Studio is just a notebook-like environment to practice different Gremlin traversals. And I have this running up on my local host. So you can see here that we're doing the chapter 6 development work from the book. Thank you so much again to FT, I believe. Yes, thank you so much, FT, for posting the link. When you pull up Studio, if you're looking at all of the book's examples, you can see here that I've got different examples for all of the different chapters that we have in the book, where chapters 10 and 12 show you exactly how Netflix uses graph technology to load recommendations in prod. another talk for another time. Maybe David will have me back to do that one some other time. So during this, what we're going to do, step 1 for creating the graph schema, we just did over in the slides. And so this is the code here for creating the vertex labels. It's not a problem if I run it again. They're already in the database. It's not going to drop the data or anything like that. So then again, we're going to create edge labels. And this is all the code we just walked through. So instead of me scrolling through it, I'm just going to use the drop link up here at the top for going down to the Gremlin queries. So like I mentioned, we're going to start at a specific sensor, and we're going to walk up through neighborhoods of data to find out all of the towers that sent information to that sensor. I said that in reverse. We're going to find all of the towers that that sensor communicated with. So here's our first query. I mentioned to you that we're breaking this into 4 parts. So this first part is to ask from this sensor, where has it sent information? So for those of you who are new to the Gremlin query language, this is probably the first time you're ever seeing it. I mentioned at the very beginning that Gremlin is a functional programming language. For this example, the way that this kind of works within graph structures is that you're thinking in streams, and you're applying functions to streams of data as you're walking through your data. And that's a much different way to mentally process a query language or a programming language than traditional object-oriented programming languages like Java, C++, etc. So this is gonna look much different, but hopefully the examples are followable. On line 1 here, what we're doing is we are using the sensor's full primary key, which is 102.688, to essentially start one traverser or one gremlin on that vertex. So in my mind, I see on this query, when we say for all vertices, dev.v, find the vertex that has the label, the vertex label sensor, and then it has the sensor name of this value. And so now we have one gremlin traverser that is going to be in your graph database on that vertex. At least that's how I think about it. This .next statement here essentially processes that entire traverser and stores it as a variable called sensor. On line 3, we're going to essentially do the same thing. We're going to say for this sensor vertex, line 3 is showing you the same thing that's happening on line 1, just in a different fashion. We're going to start at that sensor vertex. And then line 4 is where we start walking, or we start moving throughout our data. We're going to start at that sensor and walk out all sends edges. And so now from that sensor, we are on all of the connected vertices, and we want to create a JSON payload. My favorite steps for creating JSON payloads in Gremlin are project by. So what I would like to do is I would like to create a JSON payload that has 2 keys. For every single vertex, I want a label and then its name. The by modulators in Gremlin are applied round robin. So this by modulator on line 6 is for the label key. So this by modulator creates the values that are going to be stored for label. And this by modulator on 7 and 8 creates the values that are going to be stored for name. So we now are at all of the vertices connected to our starting vertex. And the first thing we say is, tell me its label. So the label is going to get populated to the label key. And then the second piece of data we want to know is if it's what the tower name or the sensor name is. And now we don't know if we're on towers or sensors. So you need an if-then style of syntax. And that's what's happening on line 7 and 8. It's essentially saying, if this vertex is a tower, return the tower name. Otherwise, it's going to be a sensor, so return the sensor name. And we can go ahead and run this. And you can see this payload down here is the results of that query. We have the keys, label, and name. And we have one of these JSON objects for every single vertex that is adjacent to our starting sensor. And the value for label is sensor, which is done on line 6. And then the value for name is either going to be the sensor's key or the tower's key. And we use the if-then semantics here on 7 and 8 to determine those values. So at this point, we have started on sensor 102.688, and we've walked out one neighborhood. What we want to do now is we want to walk out two neighborhoods. So we want to repeat that process and go one more neighborhood out. We're going to start the exact same. We're going to grab our sensor vertex and store it in a variable, and that's what's happening on lines. Let me turn line numbers on. For those of you who go to use Studio in the future, pro tip, on a Mac, Control-L toggles line numbers in Studio. So that's what I'm pressing over here to turn the line numbers on. So what we're doing here is we are walking again, storing our sensor as a variable. And as I mentioned last time, what's happening on lines 1 and 2 is just a new or a different way to do the exact same thing on line 4. Those are the same statements. It's essentially saying start my traversal on one vertex. On line 5, we're doing the same process that we just walked through. We walk out one neighborhood. But now on line 6, we're asking the query to walk out a second neighborhood. So we've now taken 2 steps away from our starting sensor. And we apply the same logic. I wanna shape a JSON payload for every single vertex in the second neighborhood. And I want that JSON payload to have predictable keys. I want them to be label and name. The value for label needs to be the vertex's label. And the value for name, if it's a tower, needs to be the tower name, else it needs to be the sensor name. I know we can see it down there, and I love live demos. So because I had this line highlighted, when I pressed the run button, when I pressed the real-time execute, it was only running what I had highlighted. So I'm gonna move my cursor from highlighting and make sure it's actually running the full statement. And from that picture that we saw in the slides, we're confirming what we're expecting. We had 3 vertices in the second neighborhood. We walked from our first vertex through the first neighborhood to the second, and we expected to see white center and two other vertices, and that's what we have here. We have the white center tower, 103.7588, 106.1624, which is what we were expecting when we were looking at the picture on the last slide. I'm not seeing many questions about the Gremlin queries, so if there are, feel free to pop them in the chat. I'm always flipping between the code that we're walking through and the chat function, so happy to answer questions as we go. So this is the last time we're going to manually walk out. So we're going to walk out one more layer here, turning on my line numbers. We're going to start at our sensor. We're going to go to the first neighborhood, walk out the first neighborhood, walk out to the second neighborhood. And now we're going to walk one more time to the third neighborhood. And then we're going to inspect what is in the third neighborhood. Again, show me the tower name if it's a tower vertex. Show me the sensor name if it's a sensor vertex. Now, if we want to do this recursively, if we want to say start at the sensor and find all towers, obviously hard coding going out, like that's not a scalable query. And you don't want to have any hard-coded number of steps in your query. And yeah, Ali, we're about to do it. So let's actually remove the repeated steps now. So Ali's question was a great one. Where do we take account for previously visited towers or sensors? So that's what we're about to do. So the next query we want to do is we want to look at this pattern that we have here. And we want to recursively walk to any tower. And that query would look like this, but we're not going to run it. And because of Ali's questions is why we're not going to run it. So we're going to start at a sensor. And Gremlin has 2 steps. It's called until, it has many steps. But these 2 steps are called until repeat. And this is going to say, putting on line numbers, starting at line 4, for this sensor, until you reach a tower. I want you to keep walking out these sends edges. But Ali had a fantastic observation. Where are we going to take account for these loops? Now, I'm not going to run this because of the loops that are going to exist. You're going to end up going to a query or going to a vertex that points back to 102.688, and that's going to end up in an infinite loop, and your query will never terminate. What we need to make sure we do is remove the cycles. So I'm going to skip this one because that's a bad query. And what we're going to do is we're going to make sure we remove our cycles. And we're going to look at the exact same pattern. And there's only one step to add to ensure that we remove our cycles. We're going to start at our sensor here on line 4. The same logic. Starting at this sensor 1002.688 until you reach a tower. I want you to keep walking out these sends edges. And that's what's happening on line 6. And then Ali, your question here is brilliant. Great timing. Thank you for teeing me up. Line 7 here, the simple path step in Gremlin is exactly the step that eliminates a traverser, or it eliminates a gremlin. That's how I see them in my head. As soon as a traversal comes back to a place it's already been, it's going to eliminate it from the results. This adds memory overhead into your query now, because every single traverser now has to keep track of a state variable. So when you're thinking about the different resources that you have to make available, this one's going to end up having a little bit higher memory overhead due to every traverser now tracking state. And in that state sequence, whenever it moves to a new vertex, it checks its full state. If there is a repeat for the new vertex in that, if it's previously visited state variable, that traverser is going to terminate and no longer be considered in the traversal. So I'm going to run this, and what's happening now is we're starting from 102.688, and we're walking through every single connection in the graph until we hit a tower, and we're going to exhaust that for every single successful reach of a tower. And along the way, thousands of these traversers who ended up in these cycles were eliminated. And we can see the results down here. In DataStax graph, we use the URI format for the actual full partition key internally for how we store our data. So that's what you're seeing here in the ID field, because we didn't do all of the shaping of the JSON payload that we did, like we did in the other examples. So this is the query for how you start at a sensor and you walk out to any tower and you eliminate cycles. Awesome. Yeah, glad. Thanks, Ali. So I don't know about you, but within my teams, we have very strict and governed rules on JSON payloads in the shape of data that essentially becomes our contract when we're passing data between systems. So the real value for Gremlin is making sure you understand how to shape the payload or shape the results to ensure you're passing the right information. So this is probably one of the last Gremlin queries that we're going to get through. And so what we're adding here is we're adding back in the shaping of the results like we did previously, but we're going to be shaping things on this path object. So the last example is we're starting the exact same. Started our individual sensor until you reach a tower, keep walking out all these sends edges, and eliminate cycles as you go with the simple path step in Gremlin. Okay, awesome. At this point on line 7, we are going to have traversers that have ended up on a tower. And we want to know the journey, or we want to know the full path that they took to get to that tower. So that's what that path step is doing now. For every successful traverser that ended up at Westlake or the other towers in this example, I want that traverser to essentially put its full state into the pipeline so that we see every step it took on the way. That's what the path object is doing. And we're going to do the same thing using the if-then semantics of the by modulator. So for every vertex in this path object, I want to know if it's a tower or a sensor. And if it's a tower, I want to return the tower name. And if it's a sensor, I want to return the sensor name. And so this by modulator now is being applied to the path object. Previously, we saw it being applied to the project statement, but this is just another way to use the by modulator. So we're running through that same process, starting at sensor 102.688. We're recursively walking out to any tower and eliminating cycles on the way. Once we reach a tower, we're getting the full path object from the start to the tower. And then we are looking at the tower name along the way or the sensor name, depending on what was in that path object. If we reached, well, let's look at it, Ali. Great question on what would happen if we have multiple paths if we reached 2 towers, because we reached many towers. So on that last query, let's take a look at this JSON payload. So this first object here, this first pair of labels and objects is the first path. So the objects in this path, sorry, I didn't mean to scroll so quickly. The objects in this path start at 688, which is where we started, and this is the path that got to Georgetown. Let's look at a deeper one. We started at 688, and then we went to 508, and then we went to White Center. Third path, 688, 508, 624, 824, Rainier Valley. A little bit longer path, starts at 688, but also ends up at Rainier Valley. Let me see if I can get both of these on the screen so we can look at both of the paths. If I zoom out just one more, we might be able to see them both. One moment here. Trying to navigate this so we can look at both the paths on the same screen. So please pardon my setup change. Here we go. So if you look at these two paths, we started at 688 and we ended up at Rainier Valley, but we had a different unique set on the way. And this one went from 688 to 508, 624, 824. And then this one went from 508 to 588 and then 824. So those are two different paths that they've found for reaching Rainier Valley. Great question, Ali. Hopefully that answered what you're looking for. And you can see here that there's different towers. We discovered a longer path that reached Youngstown. And if we scroll to the bottom here, we'll probably find the longest path possible because these traversers are returned according to when they reach their destination. So we're thinking in streams. A longer path is going to take longer time to terminate and actually reach this part. So it looks like here in the back here, we had a path to West Seattle that went through 9 different sensors before it reached West Seattle. And you can see all of the different path objects here that were found. I mean, there's hundreds of ways to crawl from that. Oh, look, here's an even longer one that got to Rainier Valley. So this is just kind of an example of to investigate all of this data and find different ways, to reach the tower. So looking at time here, there are more queries. So we just kind of walked from sensors up to towers. And there's another query here in the notebook that shows you how to assign labels to your JSON payload to make it more informative, depending on how much detail you want to get with your data team on the type of JSON structure happening between this application. So they're all here in this notebook, in addition to showing you how to start from a tower and walk back down to leaves. We're not going to do all of that in the demo today. Just wanted to do a really deep dive into that part of the Gremlin query for that specific piece of this example. So I'm going to just take kind of 5 minutes to level set for all of you who hung in here. Thank you so much for going all the way through this session. Just a few items to wrap up, and then I'm happy to take questions. I absolutely love the Q&A that you all have been providing. Thank you so much. For those of you, just to kind of think back of what we've done over the past 40 minutes or so, we looked at why graph technology, and I kind of showed you some of the ways that I advise teams around the world for how to think about whether or not their problem requires connected data. We specifically walked through how sensors and towers around the Seattle area are used within the power grid to communicate voltage levels back to a centralized database for a power company in the US. And we specifically looked at their most important failure scenario, which is when towers go down, so that they're essentially making sure that they're proactively avoiding governmental compliance issues. We walked through the data structure. We went through some of your first Gremlin queries, which is a look at a functional programming language. And as I promised, I wanted to give you guys access on where you can go further with this. So you're welcome to take screenshots to make sure you have the codes, and I'll also post them here in the session in a moment in the comments. But if you would like to get 30 days of free access to the book, where it details the entire end-to-end example of what you just watched, it's chapters 6 and 7 in the book, and you can get free access to it on the O'Reilly Learning platform using this link here and the code DataStax 2020. If you are interested in maybe stepping back to an earlier use case, we have the most popular use case of graph technology available for free through DataStax at that link there. You can get a download of chapters 3 through 5, and it shows you how to build a customer 360 application. And we also build it simultaneously in Postgres, so that you can kind of do a little bit of a relational versus GraphDB bake-off. And we provide some guidance on how we think about it. Thank you so much to the attendee who provided the link to the graph book. If you want to do any of these examples, you can go here. You can use the Docker container to have everything preloaded. And we are getting ready to push out this already loaded and ready for you in DataStax desktop. So follow me on Twitter at Denise K. Gosnell if you want to look for more releases and updates to these codes and this code and examples as we're continuing to improve the experience and how easy it is to hopefully get started. And lastly, if you enjoyed walking through Gremlin and applying graph queries and graph databases to solve problems, I do this every Tuesday, actually. Every Tuesday, we are going through all of the examples in this book. It happens at 1600 GMT, noon Eastern, 9 a.m. Pacific. And if you follow the @DataStax Devs handle on Twitter, that's where you'll get the live stream notification. And I take, we kind of just make it conversational via comments on YouTube, and we're walking through all of the book's examples. And we haven't gotten to this one yet, so when we get there, you guys will already have a leg up on everyone else. So I really, really appreciate all of the questions that you guys have given me throughout the session. It has been an honor getting to be here and do this here for the Toronto Machine Learning Summit. Very appreciative of David and all the organizers and Jenny who helped me get set up today. I'm going to hang around for a bit and take your questions over here in chat. So if you want to stay, happy to have a conversation. And thank you so much. Okay, so going back to the last questions that I didn't pick up. So Andrew, is there a way to analyze the JSON result visually? I haven't considered that. What we do at DataStax is we use lambdas to govern checking the validity of our JSON payload. So we essentially are version controlling these JSON contracts with lambdas that do our validation on entry to ensure that we do have the right values in the JSON payload. But I haven't done this visually. We've just been doing it so far in code. If anyone else has another tool for visually looking at JSON, let me know. I would just be using PyCharm or another IDE to inspect the payload. Thank you, Andrew, for that question. Next question. My question is, how and who designed the network in the first place? Can we assume the path connections are reasonable? That's a very, very insightful question. So the network is set up to have a sensor outside every home and business, and that's pretty fixed. And the placement of towers are cell phone towers, and that's also pretty fixed. So what they do use these information for, what they do use these failure scenarios for, are to identify areas where we can optimize the placement of towers from the power company's perspective. Now, since we're talking about cell phone towers, the telecommunications industry has other compliance that we're collaborating with to ensure that we're using these towers to minimize both the environmental impact, but then also ensure that we have access to the data that's necessary throughout this grid, both for telecommunications and the power industry. So assuming the path and connections are reasonable, it depends on your perspective. There's a lot of people in that conversation who have certain opinions that they really want these paths to be formulated for. So within the perspective of what we're doing with the power company, what they're trying to continuously evolve is how intelligent these sensors are, because they're essentially Markovian, right? They're only passing information to a neighbor that is available to receive communication. So is there a way to more intelligently send information? Like, once you find a short path, you update the probabilities of which sensor to connect to instead of just randomly connecting to any sensor. So that's a way that we are working with using eligibility traces from deep learning to update the way that paths can converge and make a more reasonable, less random path. Yes, leave the link and the password in there. Absolutely. Great question. Going back in here into the slides, and I will put the link here. So coming in the chat is the link to the O'Reilly book for 30 days of free access, and also is the link for accessing chapters 3 through 5. You can download them as a PDF from DataStax. So great question. Thank you. Awesome. I appreciate that you thought this was a great talk. I really appreciate it. Next question, is there a way to improve performance of the query which keeps track of previously visited tower? How do you visualize the performance? That's a fantastic question. There are 2 steps in Gremlin for looking at the performance of a query. It's .profile and .explain. .profile and .explain show you every single step from query all the way down to accessing it on disk, how long it takes, and the different optimizations that happen in between. So I'm going to put those here. The steps you want to get familiar yourself with for performance are .profile and .explain for performance. Each of those will give you a detailed analysis into the steps. And if you are still here, I will show you .profile on one of the queries so that you can kind of see all of the steps that are happening. I apologize for the quick quick screen moves there. So .profile. So .profile at the end of this query is going to show you all of the performance steps and where it's taking the most time. So great question. Hopefully you still hung on there. You're still here to see. Yep. Okay, great. So .profile. No problem. Awesome. Are there any more questions? I'll continue to hang around for a bit too. If you are wanting to hop over to another session, no worries. I'm very, very appreciative, and thank you very much for coming into this session. Of course, no problem. You're welcome. Ali, how would you use the conditional probabilities between nodes to help? So that's a really, really great question. So the conditional probabilities between nodes, I would put as a property on the edge. So if you had a vertex that had 4 edges, all of those conditional probabilities would be set to be 0.25 to start. And then essentially, depending on your usage of those conditional probabilities, you would be updating them on a successful event, like you found a short path or a shorter path to somewhere else. And then you would update that probability as a property on your edge. And then when you're walking from a vertex out to others, you can choose to take the edge of highest or lowest probability, or you can also have like a dice you're rolling, and depending on the dice of equal probability, it'd be how you would choose which edge to walk through in your database. But I'd store it as a property and then use randomization to explore and walk through the graph. Great question. This is very interesting, having like one-way Q&A. But hopefully I'm able to answer your questions. I appreciate them. For those of you who are still here, I'm happy to hang around for probably another 5 or probably till about 11 or 10 or so, 11, 10 for anyone who wants to ask questions or just kind of have graph chats or any kind of chats. Happy to hang out. What tools do you prefer for visualization of graphs? That's a great question. And I think for the quick developer experience, I typically am using DataStax Studio. And yes, that's a vendor-specific example and potentially not helpful. But in DataStax Studio, you do have the ability to actually look at your graph and look at the data here. That one is not giving me the graph visualization option. So of course, I'm trying to do this live. So let me actually write you a query real quick, and we can take a look at some of the graph visualization here. And I'm going to start at a specific one so that we aren't everywhere. So here we can do out, and when we do this, we can actually look at the graph visualization of this data here in the actual tool here. And if I do out E, I will also get the edges in that visualization. Here you go. So for when I'm developing, I use DataStax Studio, and there's different ways to configure that visualization. But if I'm creating production quality visualizations, you actually can see them behind me. This visualization here, Ali, I used Gephi to create this visualization. It's a map of all of the healthcare transactions in the United States. But that's just for static one-off visualizations. For the systems that we're building, where you are creating interactive visualizations, we commonly use force-directed graphs with D3, and we just custom build them within our the front end section of our app layer. Yeah, it's a great question, Ali. David, Denise, can you visit us in person? Yes, I would be happy to visit you in person. Somehow we have to get a plane. We have to figure out planes right now during COVID, but I'd be happy to visit in person. Right, Ali, so you were talking about how you use deep learning to help you with graphs. Have you used any graph embedding techniques? Ali, that's another great question. I absolutely love your questions. Hopefully we can keep this going on Twitter. If you're on Twitter, would love to keep the fun conversation going. And I'm going to put my Twitter handle in here. Would love to chat on Twitter. But Ali, I'm going to be honest. I have not used graph embedding. I've been following that space and I find it very interesting. But I've been helping teams around the world use graph connectedness as features in their machine learning pipelines. Because the traditional tabular pipelines essentially have feature stores that you're managing to ensure that you are keeping your production models up and running. And the example we walked through here, in addition to the Netflix example, essentially is using a specific connected feature for their ML predictability model. So those features are things like, tell me the distance between these two vertices, or for this one vertex, tell me its number of connections. And we haven't needed to go as far as translating that into a graph embedding. It's going to be a fascinating space to watch emerge. But the features that I've personally been helping companies build around the world have not gone all the way to using graph embeddings. But good question. I see there's still about 15 to 20 people left in here. So if anyone has questions, I'm happy to hang out. If you are interested in doing more of these coding sessions where we walk through use cases and dive all the way through the Gremlin that helps solve them, I do this every Tuesday for an hour. We live stream it all over the world, so you are welcome to join the live stream next Tuesday so we can keep the fun going. Connected data is one of my favorite things to get to work with every day. Yeah, you're welcome. I'm really, really appreciative that you guys liked it. Thank you so much. It means the world to know that you found this valuable. Yeah, Gremlin is interesting. I've used it for a few years now, and I know Marco Rodriguez, and he's the gentleman who invented the language. And switching from object-oriented to functional programming was very difficult for me. It was an extremely steep learning curve, and I'm not gonna hide it. I've been working with it for almost 6-7 years now, so that's how I feel comfortable walking through and doing live Gremlin code. But from studying different query languages like GraphQL or SQL or the most popular languages that are emerging, it's really hard to find a better fit way to walk through graph data and explore the connectedness of your data. I know that the steep learning curve of Gremlin is going to keep it from being widely adopted. So I would really love for us to find a way to improve its ease of use, and maybe, you know, create a new language that very much applies all of the foundation of what Gremlin does, but in a way that's a little bit more friendly to people who want to use graph technology. It's definitely a passion of mine to figure out that problem. Yeah, that is a good point. SQL is also functional. I think my favorite part about Gremlin, though, to your point about CQL, is that when you look at queries like this one, where we in 4 lines we're recursively walking through all of our essentially tables, because again, data on disk, you only can talk about data structures on disk or in a certain way, and it's going to be a table. I love how the simplicity of walking through all of our tables through edges, essentially, if you were to write all of these inner join statements or left join or use the proper join tables in CQL, how large that query gets to be is astronomical. So the eloquent simplicity of Gremlin, I am a huge advocate for. And I think that the graph query language space is, you know, quickly trying to figure out the middle ground between ease of use for being able to use graph expressions for using connected data, but then also applying the fundamentals that everyone knows and loves with SQL. How does Gremlin compare with Neo4j motif language? That's a great question. I have briefly used Cypher. So I don't know if that's the language that you're referring to. And even at that point, I have primarily used Gremlin, as it's the most widely adopted graph query language by basically every vendor. And I do know that Neo4j even has a Cypher to Gremlin compiler for those of you in the audience who want to use Gremlin but use Neo4j. You can do that, but I don't have near as much experience with their languages to make an accurate comparison. So I don't want to provide a bad answer, if you don't mind. Ali, have you ever used deep learning to generate graphs? Yes, I have. That was part of my PhD. So my PhD is in machine learning, and I was studying identity on telecommunication networks. So we extracted a model of, I was working with one of the largest telecommunication providers in the United States, looking at how to use the calling and texting patterns to uniquely identify cell phone numbers, and that was done on their live network. But for the open source code that we released as a part of that project, I did have to write a data generator or a graph generator in order to do it. So yes, I did use deep learning to generate graphs. But I find that the most popular graph generation library out there is called Snap. It's the Stanford Network Analytics Platform or project. I might be misremembering the P. And the Snap project has probably the most widely adopted graph generation tool, where you can apply different distributions like scale-free distributions, random distributions, log normal, etc. And it will, according to different statistical properties, create massively distributed graph structures for you. Yep, there you go. You found it. Yeah, Snap is awesome. Snap has both data generation and also data sets and algorithms. So one of the data sets, or two of the data sets from the Snap project, we use in our book. We use the Bitcoin network to do pathfinding to a question that we had earlier in the session about how we would look at doing different applications. We use the Bitcoin weighted network to do weighted pathfinding and shortest paths to kind of talk about quantifying trust in a network, and that came from Snap. And then they also have some work on the movie recommendations project that is out there. We brought together the movie lens data and the Kaggle data to show you exactly how Netflix does movie recommendations in our book, and that's chapters 10 and 12. All of the code and data, as I mentioned, is on the GitHub repository in a Docker container and coming soon to DataStax desktop. Love the questions, Allie. If only we got to be in person, right? COVID's ruining this. We could have been great friends, or we still are, actually. Oh, thank you. I appreciate that, Allie. Let me know what you think. Leave a review if you find it valuable, or leave a bad review if it's not valuable. Whatever you think. I appreciate that. Thank you. I would love your feedback, Allie. Great. Well, I think it's almost 15 after, and there's plenty of other sessions that are incredible. David has put together a fantastic lineup for today's event. So I don't want to jeopardize or keep you all from attending some of the other speakers' amazing talks that are happening. So I'm probably going to head out here, and it looks like there's an amazing Women in AI chat that is taking place in 25 minutes. So I highly recommend people joining the chat on how we can improve diversity and inclusion across every aspect of tech, especially in machine learning operations, an area that I hope to be a part of for decades to come as I continue my career. So thank you all for the 9 of you who are still hanging in. It has been absolutely lovely getting to meet you and answer your questions. Hopefully we'll get to do this in person next time. So thank you so much. And I'll see you on Twitter or see you on Tuesdays. Cheers, everybody.